Download this code from codegive.com, link in the description below. Chapter 10 of Neural Networks literature often covers recurrent neural networks, RNNs, and their recursive variants. RNNs are a class of neural networks particularly suited for sequential data, such as time series or natural language. They work by maintaining a hidden state that can capture information about previous inputs in the sequence. In this tutorial, we'll cover the basics of recurrent neural networks, their recursive counterparts, and provide code examples using Python with tensorflow/keras. Understanding RNNs. Basics of RNNs. 1 concept: RNNs have loops in their architecture, allowing information to persist. They take an input sequence and maintain a hidden state that gets updated at each time step. 2 mathematical representation. At each time step /t /h_t equals f w_h_t1 plus w_xx_t plus b. Where /h_t is the hidden state at time /t /x_t is the input at time /t /w_h and \w_x are weight matrices. \b is a bias vector. \f is an activation function, often 10 or ReLU. Training RNNs. RNNs are trained using backpropagation through time, BPTT, which involves unfolding the network through the sequence length and applying standard backpropagation. Recursive neural networks. Recursive neural networks, rnns, are a special type of RNN that are particularly useful for structured data, such as trees. They are designed to process data that has a hierarchical structure, such as parse trees in natural language processing. The main difference between RNNs and rnns is that RNNs process sequences of inputs, while rnns process inputs that can be represented in a tree-like structure. Code example. We'll implement a simple RNN using tensorflow/keras for a sequence classification task. Let's assume we want to classify sequences of numbers. Setting up the environment. Make sure to install TensorFlow if you haven't already. Code. Explanation of the code. 1. Data generation. We create a synthetic dataset where each sequence is a series of random numbers. The target class is determined by whether the sum of the sequence exceeds a certain threshold. 2. Model definition. We define a simple sequential model with one RNN layer, simple RNN, followed by a dense layer for output. The RNN layer has 32 units, and we're using a softmax activation for binary classification. 3. Training. The model is compiled with the atom optimizer and categorical cross-entropy loss. We then fit the model to the dataset. 4. Evaluation. Finally, we evaluate the model's performance on the training data. Conclusion. This tutorial provided an overview of recurrent and recursive neural networks, highlighting their differences and applications. We implemented a simple RNN in TensorFlow/keras for sequence classification. For more complex tasks, you can explore long short-term memory networks, LSTMs, or gated recurrent units, GRUs, which are popular variants of RNNs that help mitigate issues like vanishing gradients.